All right, so you guys are now, I would say, pretty much close, like to. It all gets easier from here, from this point on, at least until we get to the final, and that's just simply because finals occur during. They suck. Okay, but that's not a function of my final being terrible. That's a function of everybody else giving their terrible finals and interfering with my great and awesome final. Okay. So I put up videos on sorting algorithms. They should all be up. There's one sorting algorithm I didn't go over because I wanted to do it on a whiteboard, and I'll be happy to show you guys in class. That particular algorithm doesn't require any of the other sorting algorithms, and that's what I'll go over today. But this is the latest assignment. Because I assume that you're not going to be working over the break, it is due the 30th, but there's also going to be other stuff that's going to be due the 30th as well, which I'll post. I'm planning today posting all of the remaining homework that is left for the course, which really isn't too much, believe it or not. So that's my goal for the day, to post basically, just so you know, for the rest of the semester, everything else you have. And it's not too much, but this one's actually not going to, this one's a bit different. So first off, you are allowed to use any programming language you want for this assignment and for any of the other assignments we have left. Okay, so if you wanted to try out Python, go ahead and try out Python. If you wanted to do R, you can do R. If you wanted to do some other language, that's great. I really only have to be able to run it on my computer, which shouldn't be that hard for me. And I mean, since you're demoing it also, that's not really too much of a concern either because of that. And this one's different because what you're demoing isn't the code necessarily. You're demoing the data you collect for this, okay? I've left it a bit abstract, so, but I do have a rubric to follow for this. So here, you're going to be implementing 3 sorting algorithms. That in itself isn't really that hard because the sorting algorithms have been done forever, and there's even code on how to do it in your book, right? So not too bad there. So you've got 3 sorting algorithms. You've got to implement insertion sort, quick sort, and then choose one other from the list below. Shell sort, merge sort, heap sort, and tim sort. Tim sort is also located in your textbook. So now you want to modify these sorting algorithms to keep track of the number of comparisons that are performed. So every time you check whether some number is greater than another number or less than another number, right? So every time you do a comparison, keep track of that. Every time you do an exchange, keep track of that. And then how long it runs. Okay, so that's 3 things you want to add into that sorting algorithm to keep track of. How many times there's a sorting comparison, how many times there's a comparison, how many times you've got to exchange stuff, and how long it's going to take to run. You can do that in, there's system.nanotime that will get the elapsed time in nanoseconds if you want. There's also the other way we've been keeping track of time throughout the semester, which does it in milliseconds. What you're going to do, so that's really the first part of this, but to show that, but what we want to do here is like sort of show how, why would we use some sorting algorithm versus other sorting algorithms? Why would we bother using insertion sort? Well, because it's actually pretty good for small amounts of data, right? It doesn't have to deal with like the overhead of doing recursion or anything like that. So so basically what you want to do is you want to get a pretty large data set. So once you have your sorting algorithms, you want to make a driver of some kind that basically creates random, creates arrays of certain sizes, 64, 128, and so on and so forth. Make them bigger and bigger and bigger. In fact, you could probably go well above 1024. In fact, I highly recommend you go well above that number. Like, try doing sorting algorithms that run into basically the hundreds of thousands or millions of data, right? And see how long they run. Let it run overnight, okay? Because what you're going to be doing is that we want you to output this data in a way that's that we can look at and say, wow, insertion sort starts out great, but then it gets really, really slow as we get more data. But quick sort, wow, that really is an apt name for it. It's quick, right? Right. So the idea here is that you want to output your data. Now, I highly recommend outputting your data in a CSV format. Does anybody know what CSV is? No. Okay. CSV is a very simple data type. It is a raw text file and it stands for comma separated values. Basically, it's just a value, and then a comma, and then a value, and then another comma, and then a value, and another comma, and so on and so forth. And it just ends with the extension .csv. And if you double-click it, it will, by default, be opened by Excel or the equivalent program on your computer. And it will import it in, and then you can start doing all those nice things with Excel, like graphing it, right? So this makes it very easy to import. It also makes it very easy to read when you're like reading it into a file or something. Of course, you can just format it in raw text as well. But you're going to have to eventually you're going to have to create graphs and stuff. Believe it or not, the toughest part of this is actually just going to be coming up with some way to display your data to me, right? You can be like a raw text format that basically clearly shows, okay, insertion algorithm or insertion sort. This is the number of exchanges that happens. These are the number of comparisons that happen. These are the number this is the amount of time it took for this input size, and then maybe the same data for that input size, and so on and so forth. So basically, getting this data into like a table or into a graph would be really, really helpful. So I can see how this works. So you get 20 points for doing it. So here's the breakdown of the score for this assignment. 20 points if you do insertion sort, 30 points if you do for quick sort, and then another 20 points for your third sorting algorithm. We emphasize quick sort because we always put we've always put partition from quick sort on the exam, so keep that in mind. The data is 15 points. Data is collected, 15 points. You present the data in a meaningful way. So you get your 70 of your points just by implementing your sorting algorithms. Then you also have to collect your data, right? Which means pretty much like outputting it to a file, which isn't that hard, right? It's like the inverse of scanner. You create like some kind of file writer that targets a file, and then you write out to your file instead of printing it out to a line. Once you can confirm that's working, right, you can basically set it up so that you are gathering a lot of data and let it run like while you go and watch TV or something, and then come back and all the data is out there for you. And then 15 points for presenting it in a meaningful way. So, right, if you collect data but it's just a mess of data, we'll give you some credit for that. And then to get your full credit on the assignment, you've got to present it in a way that actually doesn't mean I have to like sift through and figure out what your data is, right? And 7 points extra if you do TimSort as that third algorithm. Okay, so you've got a lot of flexibility in here. Again, you can do this in any programming language you want, or any, So if you want to do this in Java, like you've been doing, great. If you want to try it in C, great. If you want to try it in Python, great. Any language. Okay. Whatever makes it easier for you, or if you need to get practice in another language, that's perfectly fine. Okay, so that's what, that's what we have there. Now, today I wanted to go over the final sorting algorithm because this one is now this one is not in the book. But I really like going over this sorting algorithm because all the other sorting algorithms I've done, they're they're comparison sorting algorithms, right? In the sense that basically the way it works is that you always have to compare things, okay? Right? You have to compare one number to another, and if you see if one number is bigger than another number, you just simply put that number, so if two numbers are out of order, you just swap them essentially. That's the way all sorting algorithms work. Or at least you're led to believe, because there's ways that you can handle that. So I'm going to show you today how to do radix sort. Okay? Now radix sort is very interesting because you don't actually compare anything. Not really. And it also has this really weird runtime, which is big O of WN, right? Rather than where W is word size, I believe, or so we're just going to go ahead and run through this, and I'll show you, and then we're going to go and look at the Wikipedia page on this to take a look at it. So so unlike the other sorting algorithm, I'm going to be dealing with 3-digit numbers just to show you how this works. So give me some 3-digit numbers. Okay? 100? Okay. 961. 666. I'm going to put on a 2-digit number, 92, but I'm going to label it 092. Okay. Another number. We need 457. 457. Let's go with 3, 2, 1. And let's see, that's 1, 2, 3, 4. That's probably enough to be going on. So the way Radix sort works is that we are going to have, I'm going to create 10 queues. Okay? Rather than just, so this is very interesting. I'm going to be creating 10 queues. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Why 10 queues? Because I'm dealing with with numbers that are decimal. They have 10 possibilities for each digit. So I'm going to label each queue. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. One for each possible digit. And now to sort, what I did, so now to do this, I go through and I check the least significant digit of each of these numbers. So for 100, its least significant digit is 0, right? So I'm going to put it in the 0 queue. Okay? Then 961, its least significant digit is 1. Okay? 666, its least significant digit is 6, so it goes into the 6 queue. 092, its least significant is 2. 457 goes into here in the 7 queue, and 321 goes in the 1 queue. Okay? Make sense to everybody? And now I go through the queues in order, and I dequeue them. I completely dequeue them. So I dequeue 100 from the 0 queue, 961, 321, 092, 666, and 457. Now, that doesn't really seem to have really sorted it at all, right? That's okay, because we're not done yet. That was just the first run. We need to do 3 runs, 1 for each digit that we have, right? Because now we're going to go and look at the second digit, and we're going to throw them into queues. All right? So 100 goes into the 0 queue because its middle digit is 0. 961 is going to go into the 6 queue because its middle digit is 6. 321 goes over here because that's a 2. 092 goes over here. Okay? And 666 goes in the 6 queue. And then 457 goes in the 7 queue. Sorry, 4 goes in the 5 queue. Right, because we're going off of 5. All right, so I want to just take a look at the last digits before I erase them and dequeue again. Look at the last digits from what we just read from. 0, 1, 1, 2, 6, 7. The last digits were in order because we threw them into the queues based on what their last digits were, and then we went through the queues in order. Now when we go through, so they were sorted based on their last digit. Now if we go through the queues again, we get 100, 21, sorry, 321, 457, 961, 666, 092. So now the numbers are completely sorted with regards to their first and second digits, right? 0, 21, 57, 61, 66, 92. So if these were 2-digit numbers, they'd be sorted, right? That's pretty cool. All right, so now we have to do them in by the most significant digit, right? So we throw 100 into the 1 queue, 321 into the 3 queue, 457 into the 4 queue, 961 into the 9Q, 666 into the 6Q again, and 092 into the 2Q, and then we would just simply read them out in order, right? And notice that they are completely sorted now. And we did that without comparing any number to any other number. Okay? That's pretty nice, because what if you're dealing with a situation where you don't have the technology to basically read two numbers and compare to see which ones are bigger, right? And that's actually, a situation that people had to deal with. So let's take a look at radix sort. All right. Whoops. Not Geek for Geeks, but radix sort on Wikipedia, right? Here is a IBM card sorter, and it did radix sort on punch cards essentially. Now it was a bit difficult. Now what's great about this is that it works by not having to basically compare the and you don't have to build any mechanisms for comparing two numbers. You just have to compare the last digits so that they end up in the piles, and then set it so that you're going for the next set. Now it is O of Wn, where W is the word size, meaning how big these numbers can be, right? So, this was 3 of n for 3-digit numbers. It's 4 of n for 4-digit numbers, right? The biggest number is a 4-digit number. Now, when we're dealing with integers, now there's a reason we don't implement this. This doesn't necessarily get implemented onto computers, even though it has that nice looking O of n right on there for a sorting time algorithm. And the reason is because assume you're dealing with 32-bit integers, right? So first off, rather than having 10 Qs, we have 2 Qs because every digit's either a 0 or 1, right? And then if there's 32 bits, 32 binary digits, then that means that W is equal to 32 every single time. So that makes it a bit of a, so that can make it a bit difficult sometimes to sort. That doesn't make it difficult to sort. That just means you have 32 iterations to do, right? And that means that if your runtime is like n log n, right? If log n is 32, how big does this list have to be for an n log n to be for this to be better? Basically, the list has to be. Let me be clear here, right? O of Wn. When we're dealing with 32-bit numbers, right, this is often going to be well bigger than O of n log n for some cases, or a lot of cases actually, but let's consider this. If this is 32, right, if this is 32n, how big does the, let's go ahead and make these equivalent, okay? So if this needs to be 32n, how big does log n have to be? It needs to be 32 for them to be equivalent, right? So what that means, how big does n have to be? Well, it would have to be 2 to 32nd power, which means we'd have to be doing about 2 billion items worth of sorting for this to come out ahead. Which is a lot, but also sometimes there's a hidden constant here that for these. So radix sort isn't necessarily that bad of an algorithm. Especially since you don't actually have to do any comparisons, which again are very, very expensive. These are, again, you're having to deal with exchanges, so it's kind of apples to oranges too, right? But it exists, but it works, and it's if you're building a machine a physical machine that is going to be physically sorting stuff, right? Unless you need to have some kind of vision in the machine, like for the way it looks at stuff, this is the way to do it. Because you don't actually ever have to compare anything. You just simply say, oh, it goes into this pile, right? And you don't compare it with anything else. And I like to use queues because that's because again, this is a data structures class, so we might as well use a data. If there's a solution that uses a data structure, we're going to use the data structure, right? Then try to get along without it. So. All right, so anyway, that's the last sorting algorithm I wanted to go over, and I just thought it was very interesting because the book doesn't really cover it, even though it totally should.